I'm starting with the today's session. Welcome everyone to the NPTEL course on Introduction to Polymer Physics. The course instructor is Professor Amit Kumar, Department of Chemical Engineering, IIT Guwahati. I am the teaching assistant uh, and my name is Shikha Sharma. I am a research scholar in the Department of Chemical Engineering, IIT Guwahati. And this is a live interaction session for week 6, which is on the topic amorphous phase, crystalline phase, and mechanical properties of the polymers. I hope you have gone through the 3 lecture videos. So in this class, like we in the previous class, we have covered already the branching, the hyperbranched polymers, the number average degree of polymerization, the weight average degree of polymerization, branching and how the network form and how the dendrimers and uh, how the because of the cross linking the network form and how the gelation happens. And then we discussed about the gelation and swelling of the network polymers. We discussed about the mean field model of gelation, scaling model of gelation. Then we discussed about the Flory-Renner equation. We solved some of the numericals and we discussed some of the concepts regarding uh, all these topics in the previous class. Today, in the today's class or in the today's live interaction session, we will be discussing the topics such as crystalline polymer phase, amorphous polymer phase, mechanical properties of the polymers, and we will try to discuss some of the important concepts, and then we will simultaneously solve the numerical problems. And if you have any doubt so far, you can discuss. And if you have any query in the today's lecture also, you can please feel free to ask. So let's start with the today's question number 1, which is a concept question that the polymeric molecules dash a definite crystalline structure. So the polymeric molecules, they either have, do not have, completely have, or partially have a definite crystalline structure. So this is a very simple question. Can anyone please answer this question? The polymers, they are made up of, like their structure is basically crystalline or not? Any answer? Have crystalline? No, actually what happens is no polymer is 100% crystalline or 100% amorphous. The polymer is actually a mixture of 60% crystalline and 40% amorphous. Mostly it will be like crystalline 60% and 40% amorphous. So the it is the combination of both of these, not like it is having the crystalline structure, but it is not having the completely crystalline. It is having some of the region will be the crystalline and some will be the amorphous region. So this is the how the amorphous looks like, and this is how the crystalline looks like. So we know that crystalline crystalline polymer is basically the region in the polymer which is crystalline is basically in that there is a they will be able to pack closely in perfect parallel alignment, and they have basically the ordered structure. So the polymeric chains, they will be in the crystalline polymer. The polymeric chains, they are in the ordered lamellar structure, and they exhibit the fibrous behavior. Like they have the orders, they are in the order they are arranged, while in the amorphous polymers they are composed of the unordered amorphous region, unordered or amorphous region. They are not having the ordered region. So this is what we are discussing, the basic concept and the difference between the amorphous polymer and the crystalline polymer. So in the amorphous polymer, it is composed of the unordered or the amorphous region where the molecules are randomly arranged, and that randomness is induced basically by the thermal fluctuations. Also, in the amorphous polymer, there is the concept of glass transition. Like what happens? There is a term known as glass transition temperature. So what happens? What is the glass transition? So the amorphous polymer, they are in the glassy state below the glass transition temperature, like below Tg or below glass transition temperature. Polymers will be in the when it is in amorphous polymer, it will be in the glassy state, which is the stiff, hard, and brittle. While above glass transition temperature, polymers are in the rubbery state, which means it has low hardness. So there is the concept of glass transition in the amorphous polymer, not in the crystalline polymer. Also, the atactic with group bulky group polymer, they form the amorphous polymers. They form the amorphous region. The polymers which are like they are in atactic, and the bulky group is there. So because of the bulky group, there is not a formation of the there is not the formation of a regular structure, and there will be more of the, because of the uh, mm, like the hindrance or the resistance, there will be more of the randomly arranged structure of the polymer. So the atactic with bulky group polymers, they forms the amorphous polymer. Some examples of the amorphous polymers are polystyrene and polycarbonate. So we understood that amorphous polymers, they are basically the unordered or the amorphous polymers which are not arranged in a regular or the uh, uh, closely packed or the perfect structure. They are randomly arranged, and there in the amorphous polymer there is this concept of the glass transition. What happens in the glass transition? Below the glass transition temperature, it will be in the glassy state, and after the Tg, which is the above the Tg, which is the glass transition temperature, above that particular temperature, it will be in the rubbery state, right? Whereas in the crystalline polymers, what happens? They are packed closely, and they have the perfect alignment. They are basically arranged in the ordered laminar structure. So what happens? Like this, they have lamellas in the crystalline polymer, right? So properly the chain is arranged, and the crystalline polymers, the 100% crystalline polymers, we can achieve from the solid state polymerization method. So we are just discussing the basic concept of the crystalline polymer. And also in the crystalline polymer, there are the formation of the crystals. Crystal structure is there. So the crystal can be of any structure. The units can be of any arrangement, like it can be orthorhombic or triclinic or monoclinic. When we see through the XRD or the electron microscopy, we can see that the crystal structure can be of any type. Also, it has a concept of melting transition, means when the temperature is increased, the crystalline polymer, it will melt and it will start flowing, and it doesn't but in the case of the amorphous polymer, when we increase the temperature, there is the glassy to rubbery transition, right? But in the crystalline polymer, when it is being heated, then it will start flowing, because the polymeric chains, they will come in the proper alignment. The bonds will break, and the interlink will break, and it will start flowing. Also, the isotactic, syndiotic, and atactic, with the smaller group or the flexible group polymers, they are the crystalline in nature, right? So this is the basic concept. I am just trying to refresh the concept which we have gone through in the lecture slides. So next question is, which feature of spherulites can be observed under polarized light? Isotropic regions, bright and dark regions, C is amorphous zones, D is homogeneous structures. So what is the answer? So first of all, the spherulites, they are basically formed in the crystalline polymers, right? First, what happens? There is this nucleation will be there in the crystalline polymers, and then because of nucleation the crystal will form, that because of the nucleation and the growth of the growth the crystal will form, right, of the different it can be of different structure, like it can be monoclinic or the triclinic or the orthorhombic. But after the when the crystal will form, after that the different crystals will form, right? Many crystals will form, and then it will arrange in the lamellar structure. And uh, and when we see the bigger picture, the crystalline polymers, they are mostly in the spherulites form when we see through the polarized light microscopy, right? So what do you think, which is the correct answer? The spherulites, when we put it into the polarized light microscopy, how it looks like? Yes, yes, you are correct. So bright and dark regions will form, like on the picture on the we can see on the right hand side that this is the spherulites. When we put the crystalline polymer in the polarized light microscopy, this kind of the structure will be there. In this, there are some bright regions and some are dark regions. So these spherulites, they are basically formed during the crystallization, right? And its formation is influenced by the following factors, such as the cooling rate, the polymer molecular weight, and the presence of the nucleating agent. So how the spherulite will form, it will be dependent on the cooling rate, the polymer molecular weight, and the nucleating agents. Third is the temperature of the crystallization. It is very, very important because it affects the size of the spherulites. Because if we cool at the higher rate, then what happens? The large number of the nuclei will form and more smaller spherulites will form, right? And also this bright and dark regions, it is also known as Maltese cross pattern. We also known as this Maltese cross pattern, right? Next is, as the crystallinity increases, the brittleness of the polymer increases, decreases, moderate, remains constant. So, what is the correct answer? We just now discussed that the crystallinity increases, that if something is more crystalline means it is in the closely packed or the more ordered, the polymer will be packed in more of the ordered structure. So its brittleness, it will increase or decrease, or moderate, it will all remains constant. Anybody? Increase, as you say, the answer is correct, because when we increase the crystallinity of the polymer, the brittleness also increases. Also, because also the strength and the chemical resistance of the polymer increases. Why? Because the as polymer will be in the more of the ordered structure. The crystals will be more ordered. The chains are not randomly arranged. It is in the perfect order. So its brittleness will be very, very high. Also, its melting temperature will also be very high because it is in the closely packed ordered structure. Which of the following is true at a first order thermodynamic transition? Volume is continuous, enthalpy is continuous, Gibbs free energy is continuous, or the entropy is continuous, which is true for first order thermodynamic transition. So in the first order thermodynamic transition, what happens? The Gibbs free energy is continuous. Okay, what happens is in the first order thermodynamic transitions, the first derivatives of the free energy or the Gibbs free energy, which are the volume, enthalpy, and the entropy. Volume, enthalpy, and entropy, which is the formula volume this, which is del G, which is the Gibbs free energy, by del P, which is the pressure at constant temperature. This is the first derivative of volume. This is the enthalpy, first derivative of enthalpy, and this is the entropy formula, right? So these are at the first derivative, they are discontinuous and they'll change abruptly. So when we see in the graph on the x-axis is temperature, the y-axis is the first derivative of the Gibbs free energy, which are volume, enthalpy, and entropy. As we see, this is the Gibbs free energy. So their first derivative, volume, here G, H, which is enthalpy. Here G is first derivative, then the entropy. So when we plot the graph with respect to temperature and the first derivative of free energies, we see that at the temperature below the melting temperature, what happens is there is this line, right? Which means that it is constantly with a linear rate, sorry, a constant rate or a linear rate, it is increasing. But when there is when it achieves the Tm, which is the melting temperature, then what happens? There is this discontinuity, and then it again after above the Tm, it increases with the different rate, right? So because there is this discontinuity, the option A, volume is continuous, cannot be correct, right? It cannot be correct. Enthalpy also cannot be correct, and entropy cannot be correct. Only the Gibbs free energy will be continuous. Understood? Are you following? So let's move to the next question. Glass transition has characteristics of a zero order transition, first order transition, second order transition, third order transition. So it is also the question of the thermodynamic transition, right? So the Tg, which is the glass transition temperature or the glass transition, it is a first order transition, zero order, second order, third order transition, where what happens? The polymer, it will go from the glassy to the rubbery state. First order you are saying. But the answer is second order transition. Why? Let's see the answer, the reason. Because what happens in the second or the glass transition is a second order transition because the free energy and its first derivatives. First derivatives are volume, enthalpy, and the entropy. They are continuous in this case, right? Whereas the second derivatives of the free energy are discontinuous, like the thermal expansion coefficient alpha, isothermal compressibility, and the heat capacity. So the second derivatives of the free energy, which are the thermal expansion coefficient, isothermal compressibility, and the heat capacity, they they are discontinuous, whereas the first derivatives, which are the volume, enthalpy, and entropy, they are continuous. So it is this glass transition will mostly behave like a second order transition. Also, we can see in the graph above that the volume, enthalpy, and the entropy, it is actually increasing, and after the Tg, it will again increase, but at a much rapid rate. The slope of the graph is changed, but the graph is continuous. But if we see the second derivative quantities, which are the thermal expansion coefficient, isothermal compressibility, and the heat capacity on the y-axis, whereas temperature on the x-axis, it is increasing with some rate. Then there is this discontinuity, this region, this discontinuous region is there, and then it will increase again with some different rate, right? So the option C is correct, because glass transition also exhibits this kind of the character. But because like the we also say that the glass transition is not true thermodynamic transition, right? Because there is no transition like solid liquid or the liquid gas transition, but there is a transition in the polymer melts and the not in the solid liquid gas transition. So we also says that it is not a true thermodynamic transition, but it somewhat behaves like second order transition. So we corrected option C. Next question is, presence of flexible pendant groups dash the glass transition of the polymer. So if there is a flexible pendant group, so the what happens to the glass transition of the polymer? Whereas if there is a bulky group or the stiff group, then what happens? So option A, reduces, increases, B, increases, reduces, C, constant, reduces, D, increases, constant. So we are saying B is the correct answer. So let's first discuss the concept behind it, right? वैसे option A is correct. Let's see why the option A is correct. Like it is saying that the presence of the flexible pendant group reduces the glass transition of the polymer, whereas the bulky group or the stiff group, if it is there, it will increase the glass transition temperature. Why? Because the glass transition temperature of a polymer is influenced by several parameters such as the chain flexibility, the molecular structure or the steric effects. Third is the molecular weight. Fourth is the branching and the cross-linking. So, if the chain is highly flexible, so what happens? Tg will be low. So, as we have in the question that flexible pendant group decreases the Tg, and if there is a rigid uh, group or the stiffer bulky group, then the Tg will be higher, which is glass transition temperature will be higher. Why? Because the chain flexibility all depends on the rotation or the torsion of the skeletal bonds. Chain which are made up of the bonds, bond sequences which are able to rotate easily are flexible, and hence the polymer containing the CH2 group or the CH2O group or the SiO-Si linkages, it will have the low value of the Tg. So you understood? So it will the flex the if there is will be more flexibility, that means there is a more rotation of the bonds, right? Like CH2 bond, CH2O bond, SiO-Si links, they will have the low Tg value. While the value of the Tg increases when there is a insertion of the stiffened group in the chain because of the impeding rotation. Because there is no rotation, the rotation is restricted, so the Tg will be more, since more thermal energy is required to set the chain in the motion. Example, the paraphenylene ring. This, right? So what happens is when there is a bulky group or the stiff group in the chain, then the motion or the rotation will be restricted. So it will require more thermal energy so that the chain will be in the motion state. Whereas if there is a flexible group or the uh, like it'll rotate easily. So what will happen will require less temperature. So the value will of the Tg will be low for setting the chain into the motion, right? Also, the Tg value depends on the molecular weight. If the molecular weight will be higher, then the Tg will be higher. And we can calculate the weight fraction in the copolymers and the miscible blends using the Fox equation and the Gordon-Taylor equation. Branching and the cross-linking, if there will be less branching and less cross-linking, what happens? There will be more of the free volume, so Tg will be lesser, right? So this concept we are discussing just to understand that what are the different factors on which Tg depends or the glass transition temperature depends. So now we can see, yeah, so we can see here that presence of the flexible pendant group reduces the Tg, whereas if there is a bulky group, then increases the Tg value because there is restricted motion, right? In general, factors that increase the energy required for the onset of the molecular motion increases the Tg, and those that decreases the energy requirement lower the Tg, right? Just now we discussed the flexible pendant groups, it act as the inherent diluents. So they are inherent diluents, so there will be less frictional interaction between the chains, so Tg will be lower. Whereas in the bulky or the stiff side groups, the interchain friction will be higher. So interchain friction and the energy requirement will be higher for the molecular motion, so Tg will be higher. You understood this concept? So let's move to the next question, which is on which is on free volume. As temperature decreases, free volume increases, decreases, remains constant, none. So when the temperature decreases, what happens to free volume? Free volume is nothing but the empty space between the molecules. When there is the left out space, um, when the polymer is there and there is the left out space, uh, which is like the polymer chains occupy the space, right? So there will be some kind of some space which are empty. So that is the free volume. So it in as the temperature decreases, free volume. So you are saying decreases, which is correct. Let's understand the reason why. So when the temperature decreases, so what happens? Free volume also decreases. As a result, there is restricted motion of the polymeric chain, because when there is less temperature, the polymeric chain motion will be restricted and the free volume also will be lesser. Above Tg or the glass transition temperature, there is plenty of the free volume which facilitates molecular long range segmental motion, and reduced temperature decreases the free volume, which makes the polymeric chain movement more difficult, right? So when there is that high Tg, above Tg, the glass transition temperature, the free volume is more because we have the long range segmental motion. And at the low temperature, The free volume will be less because the polymeric chain movement will be restricted. It is difficult for the polymeric chain to move at the low temperature. So Tg, which is the glass transition temperature, is the critical temperature point below which the polymeric chain motion restricts. Because the temperature is low, the polymeric chain motion will be the restricted form, and a frozen kind of configuration will be achieved. Also, there is not enough free volume for significant molecular motion. Like we see in the graph, there this Tg, the graph between the temperature and the specific volume, this point, this is the Tg. So below this, below the glass transition temperature, the volume increases with some rate. After the Tg, which is the glass transition temperature, the volume increases at a very fast rate because of the free or the long range segmental motion, right? Here at the lower side, the segmental motion of the polymeric chain is restricted, right? So if we see, plot the graph, uh, this is the below graph is below line is indicating the polymer volume. So polymeric volume is constant, right? At below glass transition temperature and the above glass transition temperature. So this space is fixed. The rate of increment is the constant rate, whereas if we see the free volume, then it will be more at above the glass transition temperature because of the more or the long range segmental motion. Below it is in the frozen configuration. The chains are in the frozen configuration. Understood? Yes, please. Yeah, yeah, true, true. As you said, at the low temperature or the low thermal energy, the packed structure will be there, right? Because everything is in the frozen state, right? Or the packed state. Yes, your point is correct. So let's move to the next question. The glass transition temperature of the two homopolymers A and B are 320 and the 400 Kelvin respectively. If we are making a miscible blend which is having A and the B homopolymer, then the glass transition temperature of 350 Kelvin is achieved according to the Fox equation. Sorry, Fox equation. So we need to calculate the weight fraction of the homopolymer A in the blend. So this is a numerical problem. We are mixing homopolymer A and homopolymer B to form a miscible blend, and we are having their glass transition temperature of homopolymer A and B, also the miscible blend uh, glass transition temperature, and we need to calculate in the final miscible blend what is the weight fraction of the homopolymer A. So please try to solve this. We need, yes. So your answer is 0.57. Have you applied the Fox equation? Yes, so your answer is definitely correct. As per the Fox equation, what it says, 1 upon Tg of the blend, which is 1 upon glass transition temperature of the blend, is equals to weight fraction of the homopolymer A divided by its glass transition temperature plus weight fraction of the homopolymer B divided by its glass transition temperature. So the and here the temperature will put in the Kelvin. So as it is given in the question that the miscible blend glass transition temperature is 350 Kelvin. So we can put 1 upon 350 is equal to weight fraction of the homopolymer A, which is WA, divided by 320, which is the glass transition temperature of the homopolymer A, right? Which is 320 Kelvin. Now plus 1 minus WA, which is one we can say that the weight fraction of the homopolymer A plus weight fraction of homopolymer B is equal to 1. So in place of WB, which is the weight fraction of the homopolymer B, is equal to 1 minus WA. So we can put in place of the WB, which is the weight fraction of homopolymer B, is equals to 1 minus weight fraction of homopolymer A divided by the glass transition temperature of the homopolymer B, which is it's given as 400 Kelvin, right? So we can put here 400 Kelvin, and we just need to simplify this. What we can do is we can solve this, right? Here it's 320 into 400. If we simplify it, we'll get this, and when we further simplify and calculate, we get 0.5715. As you said correctly, the weight fraction of the homopolymer A in the blend is 0.5715. So next question is, a polymer has a glass transition temperature which is the 330 Kelvin. A low molar mass plasticizer is added to lower the Tg of this polymer to 290 Kelvin. So we have one polymer. Its glass transition temperature is given as 330 Kelvin. And then what we are doing, we are adding a plasticizer, and it is what it is doing, it is decreasing the glass transition temperature of this polymer, which is 290 Kelvin. It bringing it from 330 to 290. If the weight fraction of the plasticizer that needs to be added to achieve this effect is 0.25, so we need to find the glass transition temperature of the plasticizer according to the Fox equation. So what we are doing, we have one polymer and it is having some glass transition temperature, and when we are adding the plasticizer, its glass transition temperature decreases, and the weight fraction what we have added is also given, and we need to calculate the glass transition of plasticizer. So we just now applied the Fox equation, right? The Fox equation is 1 upon Tg blend, which is 1 upon glass transition temperature of the blend, is equals to W1, which is weight fraction of the one component, which is here we are taking the plasticizer as first component, divide by the glass transition temperature of the plasticizer, plus W2, which is the pure polymer. So weight fraction of pure polymer divided by glass transition temperature of the pure polymer is equals to W1, which is the weight fraction of the plasticizer divided by glass transition temperature of the plasticizer, plus 1 minus the plasticizer weight fraction divided by the glass transition temperature of the polymer. So we know that we are here also we are taking that the plasticizer and the pure polymer weight fraction is sum is equals to 1. So we are replacing all this whole equation in the terms of W1, which is the weight fraction of the plasticizer. Since we need to calculate this value, it's we need, because it's given in the question W1, but which is the weight fraction of the plasticizer is given, right? So we can just simplify the equation in terms of weight fraction of the plasticizer. So we can put 1 upon 290, which is 1 upon the glass transition temperature of the blend, which is here low molar mass plasticizer is added to lower the Tg of the polymer. So final blend Tg is nothing but 290, right? So 1 upon 290 is equals to weight fraction of the plasticizer, which is 0.25. Here it's given in the question. So we can just put here. So 1 minus the plasticizer weight fraction, which is 1 minus 0.25, which is nothing but 0.75, right? Here, since the glass transition temperature of the plasticizer is unknown, so we are not putting here in the equation, and the glass transition temperature of the polymer is given as 330. So we are putting this, right? Let's just solve this. We are bringing the glass transition temperature, this term, the plasticizer term, here on the left hand side, which is 0.25 by Tg1, which is the plasticizer. Glass transition temperature is equal to 1 upon 290 minus 0.75 by 330. So what we can do is we can simplify the right hand side part and we can reciprocate, and we can get the glass transition temperature of the plasticizer as 0.25 into 290 into 330 divided by 330 minus 290 into 0.75, which is nothing but, when we solve, we get around 213 Kelvin. So are you solving this question with me? Did you get the same answer? You got some other answer, 120. But this is the answer where you did what word? Can you repeat? 180 you are getting. So where you did the mistake? Okay, okay. Okay. So next time, please, while putting the values in the formula, please take care that you are putting all the correct values. Let's move to the next question. The amount of low molecular weight plasticizer with a Tg of minus 60 degree Celsius that must be added to nylon 6 to reduce its Tg from 50 degree to 30 degree Celsius. So it is saying that the glass transition temperature of a plasticizer is minus 60 degree Celsius, and it is being added to nylon 6, and the glass transition temperature of the nylon 6 is reduced from 50 degree Celsius to 30 degree Celsius. So we need to calculate the amount of the plasticizer we have added, right? Please try to solve this question. So 18%. So we are getting it as 12.78%. Let's see where we are doing, like how we are solving. Again, we will apply the same equation, which is the Fox equation, which is 1 upon glass transition of the blend temperature is equals to weight fraction of the A component divided by the glass transition temperature of the A component plus weight fraction of the B component divided by the glass transition temperature of B component. So here everything is given in degree Celsius. So we need to convert into the Kelvin. This degree Celsius should be converted into the Kelvin, right? So 1 upon the blend glass transition temperature, which is the, after adding we get 30 degree Celsius, which is 30 plus 273 is Tg of the blend. So 1 upon 30 plus 273, which is nothing but 1 upon 303, right? Is equals to 1 minus WB, as we know that WA, the weight fraction of the component A, plus the weight fraction of the component B is nothing but it is equals to 1, right? So we are just converting WA is equals to 1 minus WB divided by its glass transition temperature, which is the nylon 6, which is a polymer. Here A is the pure polymer. So we are putting 50, which is 50 plus 273, which is nothing but 323, right? Plus WB, which is the weight fraction of the plasticizer, divided by its glass transition temperature, which is nothing but minus 60. So we are putting minus 60 plus 273, which is nothing but 213 Kelvin. So when we solve this, we will get 12.78% as our answer, which is nothing but it is the amount 12.78 is the amount of the low molecular weight plasticizer which we are adding to the nylon 6 to decrease its glass transition from 50 to 30 degrees Celsius. And the plasticizer is having the Tg is minus 60. So you understood? Are you following? So let's move to the next question. A linear poly, yes, which equation? Yes, but here we need to solve like we are solving by Fox equation because we are solving for the miscible blends we are solving. For let's like we discussed in the previous class, sorry, previous slides that Gordon and the Taylor equation is used mostly in like in case of the copolymers. Here we are just simply putting the Fox equation and we are getting the answer, right? Because we are seeing this also everywhere that we need to apply the Fox equation, like right? Studying for the Fox equation, and our target is actually to understand the Fox equation because it is mostly used. So can we move to the next question? A linear polymer with the number average molecular weight is given of the polymer. The linear polymer is having 10,000 gram per mole as its number average molecular weight and its glass transition temperature is 400 Kelvin, and another sample of the same linear polymer which is having the double or the two times of the number average molecular weight 20,000 gram per mole, and its glass transition temperature is the 430 Kelvin. So when we are making the branched sample of the same polymer which is having the molecular weight as 15,000 gram per mole, then and in that case a glass transition temperature we are getting as 395 Kelvin. So we need to calculate the average number of the ends per chain of the branched sample. So how to approach this question? So for a linear polymer, this is the equation for the Tg, for calculating the Tg in terms of the weight, sorry, number average molecular weight. When we have the number average molecular weight, we calculate the glass transition temperature in this form, right? So Tg, which is the glass transition temperature of the polymer, is equals to Tg infinity, which is the glass transition temperature of the polymer having the infinite molar mass, and here minus 2 into the density of the polymer multiply by the Avogadro number multiply by the theta, which is the contribution of one chain and to the free volume, divide by the thermal expansion coefficient of the free volume, and then the multiply by the, in the denominator it's number average molecular weight. So this is the formula which is already there in the lecture slides if you have gone through, right? So we are considering this value minus 2 rho Avogadro number multiplied by theta divided by the thermal expansion coefficient, this term, whole term, we are converting it into K. We are assuming it as K. So Tg is equals to Tg infinity plus K plus, sorry, K divided by number average molecular weight. So this, for this equation is directly like telling the relation between the glass transition temperature and the number average molecular weight. And let's solve the further this question. This is for the linear polymer. This is for the linear polymer, this formula. Why we are in this 2 is there in the linear polymer case? Because for a linear polymer there are two chain and groups, right? There are two sides, at the two sides, like here, at the here and here, there are the two and open groups, right? And groups. So 2 is there for linear group. So this is the formula for linear group. So this Mn, which is the number average molecular weight, linear, and then we have the its glass transition temperature, and for the second linear polymer we have the values. So what we can do is we can just put, and we will have two different equations, right? For linear polymer. So for molecular weight 10,000 and Tg 400 Kelvin, we can put the glass transition temperature as 400 is equal to Tg infinity plus K by the number average molecular weight, which is 10,000. This is the equation 1. Then we can, for the linear polymer, we can make the equation 2 is equals to Tg, which is the glass transition temperature as 430 is equal to glass transition temperature at infinity plus K by the number average molecular weight, which is 20,000. Now what we can do, we can subtract equation 1 and 2. Like, sorry, here it's from 2 we are subtracting 1, which is 430, here 430 minus 400 is equals to this Tg infinity we cancel out, and we'll get K by 2000, 20,000 minus K by 10,000, right here. Now we can solve this and we can get the value of, because we are just having one unknown which is K, so we can calculate K as this minus 6 lakh, right? And in the previous slide we have assumed that K is nothing but this value, right? So we can put K is equals to minus 2 rho NAV, which is the Avogadro number multiplied by the theta contribution, which is y divided by thermal expansion coefficient, is equals to minus 6 lakh. So minus minus remove, and this from 2 will divide this. We get this value as 3 lakhs, right? Now we'll apply the formula for the same formula for the branched polymers. So for branched polymers, Tg is equals to Tg infinity. Sorry, 30,000. Yeah, this is 30,000. Please, can you solve this? So here it is 10 missing, right? You are saying this, right? So it will be divided by 2, so 3 lakhs. So 10 is missing. It is a typing error, right? So for a branched polymer, the formula is Tg is equals to Tg infinity minus, here in case of 2 we are taking y, because in the branched polymer there are many number of the, like the number of the ends per chain will be different, right? It will not be 2. So multiply by rho into Avogadro number into theta divided by the thermal expansion coefficient multiplied by number average molecular weight. Just the form in the formula here, in the case of like we were taking 2 number of the ends per chain in the linear polymer, but in the branch polymer we are taking it as y. So the rest we are taking it as k, like we assumed the k, right? So k is, so k we assumed minus 2 rho Avogadro number into theta divided by thermal expansion coefficient. So minus k by 2 will be nothing but this, right? Which we just calculated in the previous slide, the value. So Tg, which is the glass transition temperature of the polymer, is equal to Tg at the infinity molar mass plus y by, because minus minus plus, so plus y k by 2 mn bar, right? So this is the what the equation is formed. Now we are putting from the equation 1, the value of Tg in this equation. So we can see in the equation 1, Tg 400 is equal to Tg infinity plus k by 10,000, right? So Tg infinity is nothing but 400 minus k by 10,000. So we can put this Tg value here in the equation. So we will get Tg of the branched polymer, which is given in the question as 395, like this. It is given 395, which is having the molar mass as 50, sorry, the number average molecular weight as 15,000. So 395 is equal to, here we are putting directly the value as this Tg value, right? Tg infinity value is equals to 400 minus this k divided by 10,000 plus the second term yk divided by 2 into its number average molecular weight, which is 15,000. So when we solve, we will get 400 minus k by 10,000 multiply 1 minus y by 3. So from, like when we simplify this, we will get this k, this value k by 10,000 multiply by 1 minus y by 3 is equals to nothing but this will value will be going to equals to 5, because 400 minus 395 will give 5. So 3 minus y, 3, this 3 will come here. So 3 minus y divided by 3 is equal to 5 into this term will go here. So 10,000 divided by k. So k value we know, when we simplify we will get nothing but this value, 3 plus 0.25 phi equals to 3 3.25. So 3.25 are the number of ends per chain in a branched polymer. So have you understood the question? Is there any confusion? So let's move to the next question. The density of the fully crystalline polymer sample is 0.95 gram per centimeter cube. The mass fraction degree of crystallinity of a semi-crystalline sample of the same polymer having a density of 0.9 gram per centimeter cube is 0.4. The density of the completely amorphous sample of the same polymer we need to find. So this is the question of degree of crystallinity, right? So density of the fully crystalline polymer is given. The mass fraction degree of crystallinity of the semi-crystalline sample of the same polymer having the density is this. So we have the semi-crystalline sample density as 0.9 gram per centimeter cube and its mass fraction as 0.4. Now we need to calculate if the density for the completely amorphous sample of the same polymer. So let's solve this question. So mass fraction degree of crystallinity formula is nothing but it is equals to the crystalline part density, this divided by the semi crystalline part density multiply by rho minus rho a, which is the semi crystalline part density minus amorphous part density divided by the crystalline part density rho c minus rho a, which is the amorphous part density. We the mass fraction degree of crystal which is as 0.4. So this mass fraction 0.4 is equals to rho c, which is the density of a fully crystalline polymer is 0.95 divided by 0.9, which is the degree of crystallinity for the semi-crystalline sample multiplied by 0.9, which is the for the semi-crystalline polymer density minus the amorphous part density, which we need to calculate, right? So rho A divided by the crystalline part density, which is 0.95 minus rho A, which is the amorphous part density. So we just need to solve this part. When we simplify, we get the amorphous part density is nothing but 0.87 gram per centimeter cube. So are you following? Okay, you got the same answer. Very nice. The crystals of a polymer have trigonal unit cell. So we know that a polymer crystal can be of any you can be of any unit cell structure, which is here it is trigonal, right? So here its dimensions are given as in the trigonal system. The A and B are the same, which is 2.19 nanometer, and the C is equals to 0.665 nanometer. The volume of the trigonal unit cell system is given as V equals to A square C sine 60. Each unit cell contains 18 repeat units and molar mass of each repeat unit is 100 gram per mole. The density of the crystalline polymer we need to calculate. So there is this crystalline polymer which is having the crystal of the shape of the unit cell shape is trigonal and its dimension is given and the volume formula is also given. So the volume in the volume formula what we can do is we can put these value because this is given A, B and C values are given, right? So we can put and we can get the volume at least. And after that, it is saying that each unit cell contains 18 repeat unit, right? In one unit cell, there are 18 repeat unit, and we need to we have the molar mass of the each repeat unit as 100. And now we need to calculate the density. So the density is nothing but mass by volume. Volume we can calculate from this, right? And mass it's given as 100 in 18 repeat units is given. So I have just given hint. Please calculate. Volume you are getting 2.76, which is the correct. The volume of the unit cell V equals to A square C sine 60, which is A value is given as 2.19 square into C, which is 0.665, and then sine 60 is nothing but root 3 by 2, and when we multiply we get 2.762 nanometer cube, right? But we are converting it into the centimeter system. Centimeter, when we convert, we can multiply. 1 nanometer is nothing but 10 to the power minus 7 centimeter. Hello, hello. Yeah, is the voice coming? The voice is coming, right? What we were discussing last? In this slide we were, at the last time we were in this slide, right? Okay, so we'll restart from the same slide. So we calculated the volume, right? And now we'll calculate molar mass of the repeat unit is given as 100 gram per mole, and we have we need to calculate the 18 repeat unit molar mass. So we can just multiply this by 18. So 18 into 100, but because we need to divide it by the Avogadro number, which is divide, and we get mass of the 18 repeat unit as 2.989 into 10 to the power minus 21 gram. Now, as we discussed, the density of the crystalline polymer is equals to mass by volume. So we have the mass as 2.989 into 10 to the power minus 21 divided by the volume, which is 2.762 into 10 to the power minus 21. So we get 1.0822 gram per centimeter cube as our density of the crystalline polymer. So you understood? So let's move to the next question. Estimate the fraction of the crystalline material in a sample of polyethylene of density 0.983 gram per centimeter cube. Data is given. Density of the amorphous polymer is given as amorphous polyethylene is 0.866 gram per centimeter cube. Unit cell dimensions of mobile data is turned off. You'll have to turn on Wi-Fi and connect to a network first. Sorry. Sorry for the interruption. So this question says that estimate the fraction of the crystalline material in a sample of the polyethylene of density 0.983 gram per centimeter cube. So we need to estimate the fraction of the crystalline material, right? in a sample of the polyethylene of density 0.983 gram per centimeter cube. So density of polyethylene is given, right? And density of the amorphous part is given as 0.866 gram per centimeter cube. Unit cell dimension of polyethylene crystal containing 4 CH2 groups are, the unit cell dimensions are given as A 7.41 angstrom, B 4.94 angstrom, C, which is the fiber axis, as 2.55 angstrom, and alpha, beta, gamma angle as 90 degree. So the structure of polyethylene is in below. Here the A, which is this, is 7.41, B, which is this, 4.94, and the C, which is the fiber axis, which is 2.55 angstrom, right? And the angle, which is alpha, beta, and gamma, they are at 90 degree, right? Here it's 90 degree. So let's calculate this. It is somewhat similar to the previous question. We need to calculate the crystalline material fraction. So first we can calculate the volume of the unit cell as, how to calculate the volume? We can multiply all the dimensions A, B, and C, which is 7.41 into 4.94 into 2.55, and it is in angstrom. So 1 angstrom is equals to 10 to the power minus 8 centimeter. So for 3, like it's 8 into 3, which is 24. So minus 24 centimeter cube. So after multiplication, we'll get 93.34 into 10 to the power minus 24 centimeter cube. Since the cell is containing the 4 CH2 groups, so 4 into molar mass of the CH2 divided by the Avogadro number, which is 4 into CH2, which is 12, right? And this is plus 12 into 1 plus 2 into 1, which is 12 plus 2 equals to 14. So 14 into 4 is the 4 CH2 groups molar mass divided by the Avogadro number, which is, will get 9.3 into 10 to the power minus 23 gram, right? Now one cell is containing this many grams for the 4 CH2 groups. Okay, so the density of the crystalline material is, density is equals to mass upon volume. So we have this again, mass as 9.3 into 10 to the power minus 23 gram. From here 4 CH2 mass, and then divide by the volume of one unit cell, which is, we calculated by multiplying the ABC dimension, which is 93.34 into 10 to the power minus 24 centimeter cube. So when we divide, we'll get 0.996 gram per centimeter cube as the density of the crystalline material. Now, how to calculate the crystallinity percentage? Is equals to, percentage crystallinity is equals to rho C, which is the density of the crystalline part, divided by the semi-crystalline part density, multiplied by the semi-crystalline part density minus amorphous part density, divided by the crystalline part density minus amorphous part density into 100, right? So percentage crystallinity is equals to rho C. It is given in the question as 0.996, which is the, here it is this is the density of the crystalline part we have calculated, right? So we put 0.996 divided by 0.983, which is the density which is given in the question, 0.983 for the density of the polyethylene, and then multiply by rho, which is given as 0.983 minus 0.866, which is given in the data. 0.866 is the density of the amorphous polyethylene, right? So 0.866 divided by 0.996, which is the crystalline part, which is we calculated above, density, minus में amorphous part density, which is given in the data as 0.866 multiplied by 100. So the 91% is the correct answer. So 91%, we have the fraction of the crystalline material. So you understood this question? Are you following? So let's move to the next question. The enthalpy of fusion of a polymer is found to decrease from 135.6 joule per gram to 120 joule per gram after 5 years of use. If the enthalpy of the fusion of the same polymer with 100% crystallinity is 290 joule per gram, then the loss in the crystallinity after the 5 years will be. So it is saying that enthalpy of the fusion of the polymer is given as 135.6 joule per gram. Then I am using that polymer for some use, and its enthalpy of fusion is decreasing from 135.6 to 120 joule per gram in the 5 years of use. Then it is saying that we need to understand how much of the crystallinity is lost in the 5 years, right? And it is given that enthalpy of a fusion of the same polymer with 100% crystallinity, when it is 100% crystalline, it's 290 joule per gram. So first let's discuss some concepts, that the wide angle X-ray diffraction, which is known as WA-XRD, and the DSC, which is the differential scanning calorimeter. These two techniques, they are the characterization techniques which are used to determine the degree of the crystallinity in any of the polymer. If the sample we have of any polymer, we'll either go for the wide angle X-ray diffraction or DSC for understanding the degree of crystallinity. So this first graph is we get from the XRD, wide angle XRD. In that, the y-axis is the intensity of the peaks and x-axis is the 2 theta angle, the diffraction angle value, right? So with respect to the diffraction angle, we get different peaks. So crystalline, the peak, the area under the peak of the crystalline divided by the total peak area will going to give the total, means the amorphous and the crystalline part will going to give the crystalline part or the degree of crystallinity, how much the part is crystalline. And in case of the DSC, what happens, the second curve is the output of a DSC curve. In that, the x-axis is the temperature and y-axis is the heat flow. So this is the glass transition point. This is the glass transition TG value. Here it is the TC, which is crystallization temperature, and last is the melting temperature. So in this case, how we find out in the DSC, from the DSC, how we find out the degree of crystallinity? We find out by taking the enthalpy during the crystallization. So in this crystallization, we find the peak area. What is the area? And then we divide it with the 100% crystalline. When the material is 100%, first how we run 100% crystalline polymer will take, we take the how much enthalpy of the fusion is there in that, from the peak area we get, and then what we will do, we will do the same thing for a polymeric sample. Then we divide both of the enthalpy of fusion and we get the degree of crystallinity. So in this question is also calculating degree of crystallinity by the method of TSC. So there is this enthalpy of fusion. So it is saying that the enthalpy of fusion at 100% crystallinity is given, and it is saying that in 5 years of duration it is decreasing from this to this. So we need to calculate loss in the crystallinity when the sample is put for 5 years. So anyone is solving this? So let's discuss. So in from the DSC method, we get percentage crystallinity is equals to heat of fusion of the sample during the crystallization divided by heat of fusion of 100% crystalline polymer into 100. So sample when it is in new condition, polymeric sample, it is not used before use, it is we are taking percentage crystallinity XC1 is equals to, before it was 135.6. The value is given here 135.6 joule per gram, the enthalpy of fusion, and sorry, and 290 is the enthalpy of fusion of the 100% crystalline polymer. So 135.6 divided by 290 into 100, which is nothing but 46.76% is the percentage crystallinity before use. And when after we use for 5 years, we'll apply the same formula, percentage crystallinity Xc2 is equals to 120. So from 135.6 it is decreasing, enthalpy of fusion 120 joule per gram. So 120 divided by 290, which is 100% crystalline polymer, heat of fusion into 100, which is 41.38. So we have before 46.76, after 41.38% crystallinity. So we can just subtract and we get the 5.38% as the loss in the crystallinity after 5 years of use. Understood? Are you following? So next question is viscoelastic behavior of a linear amorphous polymer is explained by 5 steps, which is given in the curve. There are these 5 steps. Here x-axis is temperature, y-axis is the modulus, and here it is the first, A to B is first, B to C is second, C to D is third, D to E is fourth region, and E to F is fifth region. So which one of the following is correct? So out of this, we need to just match which part is denoting which of the region. Like which is denoting liquid flow, rubbery plateau, glass transition, and glassy in a linear amorphous polymer. So this is a conceptual question. So the first part is denoting the glassy region. A to B is glassy region where the polymers are brittle and the modulus is very very high. We can see modulus is very high here, and it is the polymer is brittle because it is a glassy region. So in the amorphous polymer, it says that it goes from glassy to rubbery state, right? So how it goes? As the temperature increases, first it is in glassy state, which is in the brittle polymer, and its modulus is very very high. In the second region, which is the B to C, further we increase the temperature, we get this kind of the curve. In this, there is a maximum rate of declination of the modulus over the small temperature. If we are changing little bit of temperature, the modulus is decreasing here at the rapid rate, right? And then the polymer here will look like tough leather like behavior. In the third part, which is the C to D, if we see here, the modulus becomes somewhat constant. So this is known as the rubbery plateau region, and in this the polymer exhibits significant rubber-like elasticity, and the modulus becomes nearly constant, right? After this, there will be different three cases, like either it will go in the solid line or it will be like sorry, in this region it can be C2D region, can be either the solid line, it can be either in the dotted line, or it can be in the dashed line. This is the dotted line and this is the dashed line, right? And this is the solid line. So if there is this linear polymer, then there it will follow the solid line, and there the modulus decreases slowly with increase in temperature, and the length of the plateau depends on the molecular weight of the polymer. That is, if the molecular weight will be higher, the longer will be the plateau. In the case of second, which is the semi-crystalline polymer or the dotted line, the modulus depends on the degree of crystallinity. In the third, which is the third case, which is a cross-linked polymer, dashed line will be there, improved rubber elasticity with creep portion suppressed, and the region 3 remains in effect at higher temperature up to the decomposition, up to the decomposition, one second, up to the decomposition temperature. For cross-linked polymer, therefore, the region 4th and 5th does not occur. So in the dashed line, it will go directly like this, and it will not show the 4th and the 5th region. And it will happen in the case of the cross-linked polymer. Then in the 4th region, which is the D2E, is the rubbery flow region, where the polymer exhibit non-cross-linked linear polymeric chains when is more in the rubbery plateau region. In this region, the polymer exhibits both rubber elasticity and it will start flowing. So flow property will also be there, but depending on the time scale of the experiment. When subjected to the stress, then for the short time, then the entanglements of the polymeric chain are not able to relax and the material still show the rubbery behavior. But if we apply the stress for a longer duration, then and at the higher temperature the chain starts moving and we can see a visible flow. In the 5th region, the liquid flow region, at this very high temperature, at this temperature, this is very high temperature, right? The kinetic energy of the chains increased and permits them to wriggle out through entanglements rapidly and move as the individual molecule, right? And then it will have the high viscous flow, it will show. This is the melting temperature and it is always above the glass transition temperature. So this is the theory and the concept. Any doubt in this? So option D is correct. So first is the glassy region, then is the glass transition region, then rubbery plateau, fourth is the rubbery flow, fifth is the liquid flow. You understood the concept? Now, next question is the melting temperature of polyamides such as the nylon is high due to high flexible backbones, high degree of branching, bulky side groups, hydrogen bonding between the chains. So, now this is the melting temperature Tm of the polyamides such as the nylon is high because which one? B, D, D. Hydrogen bonding. Yes, you are correct. The melting temperature is basically depends on the if the chain will be highly flexible, then the temperature there will be low melting temperature. And then when there is a polar groups or the hydrogen bonding within the crystal, then the as we see in our question, more will be the melting temperature. So hydrogen chain is there, so more is the high is the Tm. Then if there is bulky side group also, the Tm will be higher, and if the chain ends and the branches is there, then it will induce some defects in the crystal and the Tm will going to low. So these are different parameters on which melting temperature depends on. Next question is the melt processing temperature of a semi-crystalline thermoplastic polymer is in between Tg and Tm equals to Tm, lower than Tm and higher than Tm. Melt processing temperature of a semi-crystalline thermoplastic polymer. You are saying option C, but actually it is not correct. Option D is correct. Why? Because Tm is the crystal when there is a crystal in the polymer melt. So what happens when the whole chain starts moving freely will be the Tm, means the whole polymer, the crystal in the polymers, they start melting and the whole polymer starts flowing freely. And mostly we take, so if we see in the graph where x-axis is the temperature, y-axis is the modulus, then at this Tm of higher than Tm, after this Tm value, this region is there where the polymers will start flow or starts to melt. Mostly for the polymers we take 50-degree higher for processing of the processing than the Tm, because they're like for evenly having the temperature, so we take even 50-degree higher than Tm. So you understood? Why not C, why D? Because after Tm only a polymer will start flow in this region. Next is the yes. Next is the equilibrium melting temperature of a linear polymer is 350 Kelvin. The if the melting temperature of the polymer having number average degree of polymerization is 10 and the melting temperature is 340 Kelvin. The melting temperature of a different polymer of the same polymer having the number average degree of polymerization as 25. So we need to calculate at 25 the Tm value. So equilibrium melting temperature value is given, and which is 350 Kelvin, right? And then we have Xn, which is the number average degree of polymerization equals to 10. At that we have Tm as 340. So we need to calculate Tm value at Xn bar 25. So let's solve this question. So we have this formula for connecting the equilibrium melting temperature and the melting temperature and of the polymer and the number average degree of polymerization, which is for linear polymer the formula is 1 upon Tm, which is 1 upon melting temperature is minus 1 upon Tm naught, which is equilibrium melting temperature, is equals to R by delta H U, which is enthalpy of fusion per mole of repeat unit, multiplied 2 divided by Xn bar, which is nothing but number average degree of polymerization. So in this formula, we have 1 upon Tm. Tm value we have that we have at X for first we are doing this for Xn bar 10. So 1 upon 340 Kelvin, which is the melting temperature when the number average degree of polymerization is 10. So 1 upon 340 minus the equilibrium melting temperature, which is 350 Kelvin given in the question, and equals to R by H delta H which is enthalpy of fusion per mole of repeat unit multiplied by 2 by xn value, xn bar, which is number average molecular weight, number average degree of polymerization as 10. So we can solve this and we can get R by enthalpy of fusion per mole of repeat unit is equals to 0.00042, right? The 0.00042 is the R by delta H U value. Now we'll apply the same formula for a polymer which is having the xn bar, which is the number average degree of polymerization as 25. So for 25 value 1 upon Tm. So we need to calculate the melting temperature of this minus 1 upon T temperature at the melting temperature at equilibrium, which is 1 upon 350. 350 is given in the question here in the data. So 1 upon 350 equals to R by delta H into 2 by 25 is the number average degree of polymerization at 25 when xn bar is equals to 25. So we have from the previous slide we have this R by delta H value as 0.00042 into 25. So this part we can solve. Everything is known, but Tm, the temperature, melting temperature when the xn bar equals to 25 is not known. So we can just simplify and we get 345.932 as Kelvin as temperature, melting temperature of the polymer when the number average degree of polymerization is equals to 25. Are you following? Can I move to the next question? So consider the melt crystallization of a polymer at time t equals to 5 hours. The mass fraction of crystallized or the solid material is Ws by W naught equals to 0.20. If the Avrami exponent, so this is the crystallization kinetics, right? This question is from crystallization kinetics. Can be taken as n equals to 2, the mass fraction of the crystallized material at 10 hours, we need to calculate 0.23, 0.35, 0.47, 0.59. So we know that for a melt crystallization of polymer, we have this Avrami equation as ln multiplied by minus ln Wl by W naught equals to ln Z plus n ln T. So here W naught is total mass of the polymer melt initially. WL is mass of the liquid remaining after the time T. N is Avrami's exponent. Value is given here N as 2, right? And Z is rate constant. So here this value is given. Yes, your answer is D. This value 0.59. So let's solve. As we know Avrami's equation ln minus ln Wl by W naught, which is a liquid, this mass of the liquid remaining after the time t divided by W naught at initial time equals to ln Z plus n ln T. So n value, which is the Avrami exponent, is given as 2 at t equals to 5 hours. We are first calculating. So the weight fraction is already given, Ws by W naught equals to 0.2. So we can calculate, this is the solid mass given, mass fraction is given. So what we can do is we can calculate the weight fraction for the liquid, which is Wl, which is 1 minus 0.2, which is 0.8. So in the equation 1 we can put ln minus ln Wl by W naught, which is 1 minus 0.2 equals to 0.8 equals to ln Z plus Z value is not given, n exponent equals to 2 ln t when t equals to 5 hours. So from this we can calculate ln z because rest are known. So z value is 0.00893. Now at 10 hours we will put the same equation. So ln minus ln wl by w naught equals to ln z plus 2 into ln t, n into ln t. So t is 10 here, n is given as 2, so this is n. ln z we have calculated, right? Here we put z value and we can calculate the left hand side part, which is wl by w naught is equals to 0.409425. So the mass fraction of the crystallized or the solid material at 10 hours equals to, here we get at 10 hours the liquid mass, right? So we need to convert it into the solid mass, which is 1 minus the liquid part, the weight fraction which we get for the liquid equals to 1 minus 0.409425. So we get 0.591 as our correct answer. What you have also got the same answer. The option D is correct here. This one. Now, Poisson's ratio is defined as the negative of the ratio of transverse strain to the longitudinal strain, transverse strain to the longitudinal stress, transverse strain to the angle of shear, transverse strain to the stress, shear stress. So this is just the concept, this formula that Poisson ratio is basically what the ratio, the negative of the ratio of, very simple question. So it is the, yeah, correct. It is the ratio of transverse strain to the longitudinal strain. Now, which of the following will have the lowest Young's modulus? Elastomers, semi-crystalline polymers, glassy polymer, polymer single crystal fiber. Lowest Young's modulus value. It's there discussed in the mechanical properties of polymers. This question is discussed. So you are correct. Elastomers, when we plot stress versus strain, the elastomers, it will have lowest Young's modulus value. Rest, when we increase the strain, sorry, when we have little bit of strain, the polymer single crystal fiber will have so much of stress. When we increase the strain to stress, this linear relation is obtained for a glassy polymer, and for semi-crystalline polymer, first it increases, then it will be constant, and then again it starts increasing. The stress is increasing. For the elastomer, the value is very, very low. If the Poisson's ratio for an elastically isotropic material is 0.525, the ratio of the Young's modulus to the bulk modulus is 2, 1.5, 1, 0.5. Poisson's ratio for an elastic isotropic material is given as 0.25. We need to calculate the ratio of Young's modulus to the bulk modulus. You are saying B. So your answer is correct. Young's modulus, the bulk modulus is nothing but it is equals to Young's modulus divided by 3 minus 3 multiply 1 minus 2 into Poisson's ratio. So E by K, which is Young's modulus divided by the bulk modulus, is nothing but it is equals to 3 1 minus 3 multiply 1 minus 2 into Poisson's ratio. So Poisson ratio is given as 0.25 into 2, which is 0.5, minus 1 is 0.5, multiplied by 3 is 1.5. Next is the impact stress strength is measured as elasticity, strength, permeability, toughness. You are saying D is the correct answer, toughness. So, yes, you are correct. The impact strength is measured as toughness. Below the glass transition temperature, the polymer breaks. The strength of the polymer increases with increase in the molecular weight. Because of the intermolecular attraction and also due to the presence of the polar group and chain length increases, so the strength is also increases. So option D is correct. Toughness. Toughness in a polymer can be inferred from Izod impact strength, depth of indentation, area under the stress strain curve, Charpy impact strength. Toughness in a polymer. How we like which from like from which we can calculate area under stress curve C you are saying. So it is having multiple correct options, which is option A, isod impact strength, area under the curve, stress strain curve, and Charpy impact strength. So what is actually the toughness? It is basically the amount of the energy per unit volume that a material can absorb before rupture, or its ability of the material to resist the cracking or the breaking under the stress. And what is the hardness? Hardness is basically the material resistance to scratch. So the area under the stress or strain, which is the first graph, gives the toughness value. So the option C is correct. Now, why option A and D correct? Because these ISOD impact strength and the Charpy impact strength, these are the methods from which we calculate the toughness in any material. This is the tests we run. So in Charpy, we notch method, what we do, we apply the strength, the load, we apply the load in the between where there is a V kind of notch is there. And here in ISOD method, what we do, we apply the impact load at the um, end of the material, where there is not notch. V notch is not there. So from these methods, we calculate. So from these methods, we calculate when we are applying any kind of stress, any kind of impact load, then um, then how much it is the material is taking time, or the material is taking the how much it can bear the strength before it goes into the cracking or the breaking under the impact load or the stress. So from these methods we calculate. So option A is also correct and option D is also correct. Next is we need to calculate this question, numerical question is there. The tensile modulus of a thermosetting polyester resin and the glass fiber are 3 GPa and 80 GPa, gigapascal. And then the tensile stress which is applied is 110 megapascal along the fiber direction on a continuous uniaxially aligned glass fiber reinforced thermosetting polyester composite with a fiber content is 60% by volume, so we need to calculate the resulting strain. So let's understand the question first. In there is this thermosetting plastic resin, and inside that there are glass fibers, and their tensile modulus are given. So when we apply the tensile stress of 110 megapascal along the fiber direction, along how the fiber is oriented, in that direction only we are applying the tensile stress, and then we need to calculate how much there will be strain in the material if the fiber is around 60% of the volume. Please calculate. So strain is equals to nothing but stress by modulus, right? So in this we need to we have the stress already as 110 megapascal tensile stress, and for calculating the strain we need to have the modulus value, right? So the modulus of the composite, which is formed from the fiber and the resin, is equals to modulus of the fiber into my volume fraction of the fiber plus modulus of the resin multiplied by the volume fraction of the resin. So the modulus of the composite is equals to 80 into 10 to the power 9, 10 to the power 9 Pascal, which is the modulus of the fiber given in the question as tensile modulus of the glass fiber equals to this 80 GPa, right? Into the 60% volume of the fiber content. So 60 divided by 100, which is nothing but 0.6 plus the volume fraction of the resin, which is 1 minus 0.6. 1 minus 0.6 because 1 minus the fiber part. So the resin will be nothing but the volume fraction will be nothing but 0.4. 1 minus 0.6 equals to 0.4 into its modulus, which is 3 into 10 to the power minus 9 Pascal given in the question, right? So we can calculate the modulus of the composite as 49.2 into 10 to the power 9 Pascal, and from in the formula of strain equals to stress by modulus, we have stress as 110 into 10 to the power 6 Pascal, divide by, we have just now calculate the modulus as 49.2 into 10 to the power 9 Pascal, which is nothing but 2 into 2.23 into 10 to the power 3 strain. So are you following? You understood? Yes. So do you have any questions so far? Any doubt? Whatever in the part, whatever we have discussed. So what are the topics we have covered today? We talked about the polymer and the different structures in it, which is the amorphous polymer phase and the crystalline polymer phase. In the amorphous polymer phase, we discussed about the thermodynamics of the glass transition, we discussed about the free volume concept, and we discussed about the glass transition temperature and um, how different factors affect it. And then we discussed about the crystalline polymer. In that we discussed about the how a crystal is formed from different units, like unit cells like orthorhombic, triclinic, monoclinic, and how a spherulite is formed and how it looks like under a polarized light microscopy, and due to the nucleation and the growth the crystallization happens, and then the formula for the degree of the crystallinity in terms of the density we discussed of the crystalline part, amorphous part, and the semi crystalline part. And then we discussed about the kinetics part of the crystallization by the help of the Avrami equation. And then we discussed about the temperature of the melting and how how are the like what are the different factors which are affecting the melting temperature. And then we discussed about the mechanical properties of the polymers, and in that we discussed about the stress, strain and their relationships, the curve of the elastomers and the stress strain curve we discussed. And the curve gives the area under the stress curve gives the toughness value. And then we discussed about the elastic deformation of the polymers, how elastically it will differ, it will deform, the strain value will be there. And then in the next class what we will be going to discuss is the viscoelasticity, the Maxwell and the Voigt models. And then will discuss in the next class about the non-Newtonian behavior and about its the polymer rheology, because the polymer, it doesn't follow the Newtonian behavior, it follows a complex behavior which is a non-Newtonian behavior. And then we'll discuss in the next class about the rubber elasticity. So please go through the 3 lecture videos for the next session, which is the week 7. And this is the YouTube link. There I'll be uploading this video lecture, and the Google Drive link is this, and where I will be uploading the PPT. You can go through anytime. And my email ID is shikhas.cl@iitg.ac.in, and you can write any doubt if you feel. Please write. Thank you so much for joining the class. This is the end of the today's class. Thank you so much.